block, loop, and a spring. Okay, we've done the block and loop. Now we're going to add a spring to it. So we have a mass, 0.95 kilograms, starts from rest at the top of an incline, height of 2.4 meters, slides without friction down the incline onto a level section of track. It then collides with the spring constant of 930 newtons per meter. What happens is it pushes against the spring collapses as it's pushing it, and then stops. And then what happens once it stops? Well, then it shoots the block back out. But at one point here, when it stopped, that's what we're interested in. So we want to find the initial energy of the block, the velocity of the block at the top of the loop again, that's good practice. Then the velocity of the block on the level section of track, that's over here. And how much will the block compress the spring before momentarily coming to a stop? What is the initial energy of the block? The block in the beginning, when it's at height h on the incline, is at rest, so all of its energy is GPE. We have our equation for GPE, it's just mgh. Put in the values, and we get 22.3 joules. Now, since this entire track is frictionless, and the spring is assumed to be a perfect spring, the total energy at any single point in this little adventure is the same. We're going to leave some stuff out because we solved all this earlier with the block and the loop. So we're just going to start with the energy conservation between this point here and this point here where you're at the top of the loop. So at this point, it's just mgh. And at the top of the loop, it's going to be mg. And what's the height here? It's twice the radius. So that's 2 times the radius of the loop. And that's, we see we have that up there, plus 1/2 mv squared loop. Once again, we divide through by m, so mass does not matter in this problem. And over here, we get all the g's on the same side by subtracting g times 2r from both sides. And what's next? We just switch the equation around because we're trying to solve for v. And over here, we factor out a g, right? Save on multiplying. Multiply both sides by 2, and then take the square root. And again, in words, what this value is, it's the square root of 2 times g times the difference in height between the initial position and the position at the top of the loop. We ran out of room on the last slide, so we'll repeat the equation here, substitute in our numbers, and get 3.60 meters per second. That's the speed right there. Now we want to find the velocity of the block on the level section of the track. And that wouldn't matter if you came down like this and found the velocity here. This velocity here will be the same as this. There's no GPE down there, we're assuming that's 0, so all the GPE of the box from the top of the incline is transformed into KE. And we're not going to set KE equal to what we found the energy. We'd rather work with the letters first and see if we can do less multiplication. So we have GPE at the top equals KE at the bottom, mgh, 1/2 mv squared. Once again, masses cancel out, so no matter how heavy that block is, it will have the same velocity. Again, we're dealing without friction here, and we're not worrying about the shape of the block or anything confusing. We're making this very straightforward. So we have GH is 1/2 v squared, switch sides, multiply both sides by 2, and you get this guy. That'll become very familiar to you the more you do physics problems, that the velocity of an object coming down from a height is the square root of 2g times the height. We then substitute in our values, and we find the velocity is 6.86 meters per second at the bottom, which is greater than the velocity we found up there. Why? Because all this energy here went into the kinetic energy at the bottom of the loop. Up here, some of that initial energy had to go into gravitational potential energy, so less was available for kinetic, so the block was slower at the top. How much will the block compress the spring before momentarily coming to a stop? The best way to do this problem, and we still have energy being conserved, is find the energy here and the energy here when the spring is fully compressed. Now, you could also work from here and set that kinetic energy over here, 1/2 mv squared, equal to the potential energy of the spring. But the problem with that approach is we had to calculate this V. So it might not be exact, it might not be precise enough. But if we use here, that's mgh. We're good. We were given h. So the point is, you can ignore all this. It's like none of this ever happened because the energy will be the same everywhere. And when we deal with energy problems, all we're interested anyway is the initial state and the final state. We don't care what happened in between. And here I have printed out what I said on the previous slide. I guess I got too excited about talking about it. We could have set the KE of the block on the level surface equal to the EPE of the spring. But that was a calculated value, not a given value. So the solution won't be as accurate due to the extra calculations, and there's more room for a mistake. That's one of the many advantages of dealing with conservation of energy. The energy at all positions is the same, and you can use any position, whichever is more convenient for you to solve your problem. So here's our conservation of energy. Here's the beginning energy, GPE at the top of the incline. And then what is our final energy? Tells us, right? The block is momentarily coming to a stop, so there is no kinetic energy left. Where did all that energy go? Into the maximum elastic potential energy of the spring, EPE. So it's equal to EPE of the compressed spring. Our equation now is mgh, that's the initial GPE there, equals 1/2 kx squared. That's the EPE for compression. We're trying to solve for x, so we switch the equation around. 1/2 kx squared is mgh. Multiply both sides by 2. And notice, the further we get into these problems, I don't give as much guidance for the algebra here. Hopefully it's getting more familiar to you. Then we divide through by k. X squared is 2 mgh divided by k. Take square roots of both sides. And here's our algebraic expression. As I've said many times before, this is most of the problem. This is the important thing. And then we go ahead and substitute in our values, and we get the spring compressing 0.219 meters, that's 21.9 centimeters, before it momentarily stops, then expands again and shoots the block right back.